In this presentation, we do a session review of the Innovation Wave Transmission, Manipulation, and Generation session. This session was the Tuesday 4A session at IMS 2020. Our group consists of John Hunt, Sunil Garam, and Zachary Sanger.
Our session is Innovative Wave Transmission, Manipulation, and Generation, chaired by Christian Dam of Ulm University and co-chaired by Jason Sorick, Raytheon Company. In this session, innovative waveguiding structures for RF generation, transmission, and manipulation are presented. These include liquid crystal-based phase manipulation, negative group delay-enabled leaky waves, loss-reduced multilayer structures, full tensor anisotropic metamaterial modeling, and picosecond pulse generation using nonlinear transmission lines. Theoretical and experimental results are presented to substantiate the interest of these techniques.
First, we'll begin talking about Session 1, a fine picosecond pulse generator based on novel SRD topology and tapered NLTLs, or nonlinear transmission lines. This presentation was authored by Muhibur Rahman and Kei Wu. The primary goal was to develop a generator with a very fine picosecond pulse width. They did this using two main components: step recovery diodes, or SRDs, and tapered nonlinear transmission lines. And the SRDs would allow you to create very small spikes. This was done through a combination of series and shunt SRDs. And the NLTLs would allow for a shorter pulse rise time and a longer fall time, which also allowed them to reduce ringing in their circuitry signal. On the right, you can see that there is a substantial reduction in ringing levels when using NLTL rather than using no NLTL. The SRD topology is very appealing because it has very few passive components other than the NLTL. Lastly, the resulting pulse generator design is super impressive because there's only a pulse duration of roughly 80 picoseconds while having a 26 picosecond full width at half maximum. Another very convenient design feature of this generator is the single resistor control for changing the pulse width of the generator. Following Session 1, we'll now move on to discussing Session 3, the negative group delay enabled artificial transmission line exhibiting squint-free dominant mode backward leaky wave radiation. This session was authored by Minning Zhu and Chung-Si Michael Wu. This presentation talked about how they were able to craft an artificial transmission line with squint-free dominant mode and backward leaky wave radiation characteristics by using a negative group delay circuit, a distributed amplifier circuit, and a composite right and left-handed transmission line. And especially for distributed amplifier circuits, they're great for transmission lines because they help with ZN and Z load matching. In the top right, we can see that the unit cell was composed primarily of this unilateral amplifier and interdigital capacitors and shorted stub inductor, which make up the composite right and left-handed transmission line, and then the two-section directional coupler based negative group delay circuit. Through the combination of these two components, you can see in the bottom right that the compositive right and left-handed transmission line combined with this negative group delay circuit created this negative group delay enabled artificial transmission line that elicits some squint-free properties with a backward leaky wave radiation. Moving on from Session 3, we're going to discuss Session 5, the equivalent circuit models for full tensor anisotropic composite right-left-handed metamaterials. This session was authored by Tsutomu Nagayama, and it primarily focused on developing an equivalent circuit model for full tensor metamaterials. The development began by using original NRI schematics and full tensor lenses to develop and understand the initial conditions of a full tensor metamaterial lens. The benefit of a full tensor NRI lens rather than just the original NRI lenses is a full tensor NRI lens can shift the position and then refocus at that new shifted position. In the top right, you can see the proposed NRI circuit model for a full tensor NRI lens, and then just directly to the right of it shows the relationships of all the parameters and those calculated values at a theta of 30 degrees. By using the original NRI lenses as a control, a circuit simulation was set up of 183 by 183 unit cell simulation where at 30 degrees you can see in the bottom right the full tensor NRI lens, after receiving the source signal, focused that signal and then was able to shift it 30 degrees and then refocus that signal after that phase shift. From the SPICE simulation results and the original versus full tensor NRI lens simulation results, we can conclude that this is a feasible approach.
Our next paper was called Liquid Crystal Based Parallel Polarized Dielectric Image Guide Phase Shifter at W-band. It presents a new phase modulation device for manipulation of the shape and direction of radiation patterns for millimeter wave antennas. Crowding of bandwidth at low frequencies is pushing development of wireless communication that operates at higher frequencies. Recent development focuses on pushing the usable RF communication band up to the millimeter wave range. Operating at these high frequencies causes several difficulties. A major one of these is that millimeter waves have significant attenuation in free space, meaning that to get detectable intensity levels, we need to increase the antenna gain. This is done by focusing the beam and steering it to point at the receiver, which can be done using an array of small antennas, each with a variable phase delay. This lets us shape the wavefronts of the microwave radiation to make the desired far field intensity pattern. This paper presents a design of a phase shifter in the W band, which is part of the millimeter wave range. Because a single antenna might need dozens or hundreds of these phase shifters, they must be cheap and mass producible. Liquid crystals are anisotropic, tunable materials. They're composed of molecules with a long axis and a short axis. Without an applied electric field, these molecules form a distorted liquid, meaning that light of any polarization will have the same phase velocity. As a DC electric field is applied, the molecules begin to arrange themselves, aligning with the applied field. Once they're aligned, the electric permittivity depends on the polarization of the incoming RF wave. If the polarization is along the long axis of the molecule, the permittivity is higher, making the wave travel slowly, while EM radiation polarized along the short axis travels faster. As shown on the bottom right with 4 electrodes, we can get any direction of the long axis, meaning we can tune permittivity anywhere between long axis and short axis values. This lets us create a variable phase delay, since slower propagation through the same thickness of material means more phase delay. There are a few key design details that contribute to this device. The design uses a dielectric structure to waveguide the RF radiation through the liquid crystal. Because the copper electrodes used to control the liquid crystal can absorb a lot of our RF signal, most liquid crystal phase modulators either use a stepped impedance design for the electrodes, which makes them much more complicated, or keeps the electrodes far away from the waveguide. Long distances increase the DC voltage needed to tune the crystal. This design gets the best of both worlds by placing the dielectric waveguide directly on the ground plane. Then the waveguide forms a mode using the real field in the dielectric and the image field formed inside the ground plane. As seen in the top right, this minimizes the E field at the dielectric ground interface, allowing us to put electrodes there without much loss. Note that in both pictures on the right, the RF wave is propagating into the page. In the bottom right, we see the 4 electrodes being used to create both horizontal and vertical long axis liquid crystal orientations. In the lower left, we can see the implementation of this device. The device starts with a radiation in a rectangular hollow waveguide, couples it into the dielectric waveguide, and then returns it to a hollow waveguide after phase modulation. Off to the lower right of the design figure, we see an unobstructed view of the waveguide, with the dielectric in gray and liquid crystal in blue. Note that the ends of the dielectric are tapered to reduce reflection when coupling between waveguides. All 4 electrodes are shown in the figure in maroon, with the top electrodes transparent so they don't obstruct our view of the device. Note that they run along the whole length of the liquid crystal, so that the whole thing will be tuned to the same long axis direction. Using the device, researchers were able to produce differential phase shifts, meaning the maximum phase delay minus the minimum phase delay, of more than 500 degrees at 110 gigahertz, which is more than 100 degrees per decibel of loss. This device is the first step toward integrating a liquid crystal phase shifter for millimeter waves in planar device architectures. which would make it much easier and cheaper to integrate into existing systems.
Last but not least, Sunil will discuss Session 4, the demonstration of low-loss RF conductor in Ka and V bands using copper-iron multilayers for 5G and millimeter wave applications.
The next few slides explain the research work demonstrating low-loss conductors for 5G applications by Renuka Borotu and Yongkyu Yoon. Before we begin, let's review authors' motivation and the purpose for their research. In the last decade, we have heard terms like IoT, Industry 4.0, self-driving cars, smart devices, and so on. For all these, communication is very critical, and the current communication standard of 4G cannot support the communication levels of these next-generation devices. 5G is an upcoming technology with higher data rates, bandwidth, frequency bands, and also leverages some features of massive MIMO antennas. Advances are also needed at device and transmission level to reduce losses like substrate dielectric loss, conductor loss, and losses due to surface roughness. For this paper, we're going to be focusing on the conductor loss. Now, let's look at conductor loss. Conductor loss is loss due to resistance in the line. In case of DC, the current flows through the entire cross-section of the conductor, but in case of alternating current, most of the current flows near the outer layer of the conductor, and this is known as skin effect. The depth of material where this current flows is known as skin depth and is given by the expression shown. Bigger skin depth means more current flow. Note the inverse relation between the skin depth and the magnetic permeability. If we can understand how to reduce the magnetic permeability, we can increase the current flowing through the conductor. The authors present an innovative way to use combination of ferromagnetic and anti-ferromagnetic materials to manipulate the effective permeability. With the right combination of materials, they were able to fine-tune the permeability for the desired frequency range. The authors conceptualized a metaconductor made of layers of copper and iron. They performed simulations to determine the effect of two parameters. One, number of layers, and the second, ratio of layer thickness. Their simulations indicate that as the number of layers increase, the resistance decreases, and adjusting the ratio of copper to iron layer thickness allows them to target different frequencies. For practical experiments, the authors chose a conductor design with 10 layers and a thickness ratio of 6. A layer thickness of 150 nanometers for copper and 25 nanometers for iron was selected, as it is much smaller than the skin depth. Next, the authors tested their device performance and a solid copper conductor for comparison using network analyzer. Here are the results. The metaconductor shows a good return loss of greater than 20 dB up to 67 GHz. In case of insertion loss, they noticed 3 different regions across the frequency range with respect to the copper conductor. As we move from low to high frequency, the metaconductor performs poorly up to 20 GHz. Then, performance starts to improve, transitioning between 20 and 30 GHz. Between 30 and 67 GHz, the metaconductor performs better than the copper conductor with maximum improvement of 0.16 dB at 51 GHz. That reflects a 32% reduction in resistance. With this, the authors have successfully demonstrated low-loss conductors in Ka and V band using copper and iron multilayers. Following are the references used for this presentation. The references also include presentation materials shared at the 2020 IEEE MTTS International Microwave Symposium. This was held virtually from August 4th through 6th of 2020.